Yeah.
You'd have to come and pick it up.
Reef guys, can you actually see me? You may be muted, by the way.
We can kind of see you, although we see ourselves more than we see you.
Am I all craziness and everything?
Oh, you're fine.
Oh, okay.
Oh, yeah.
Okay, good. All right. Share the screen and I'll go into the presentation mode and we'll have some fun with this. Because there are some good pictures in here. All right.
I brought back most of the plants in our backyard this time. Assembled rocking chair.
YouTube
Live is unwatchable? Really? This?
Yeah, I was just trying it at my desk, and then I was like, oh, you know what, I'll just...
Board's okay, but if it's unwatchable, that's bad news.
The audio keeps on dropping out.
Oh, man. All right, bye. Still, we got it going. All right.
Are you going to do Chalk Talk?
No, it kind of seems weird. Then it becomes the Chalk Talk becomes more of a podcast than a question. I like the sort of immediacy of this.
What's happening?
I'm moving to the Bay Area. I know, right? It's weird.
Maybe you should send to CGI.
Maybe. My wife has got a cool new job, and so I'm going to be moving to the Bay Area, but then coming down to every other week or so and stuff. And so the Chalk Talks will probably go to an every other week schedule from now on. Although I love doing them so much, so we'll see. We'll see if we can work it out.
Different type of relay.
A host in the Bay Area to do a Chalk Talk or something like that. Anyway, let's switch over. We're going to talk about today. We're going to have some fun. Machine learning kick, right? That's sort of obvious. But the fact that this is a rendering thing is super cool. I'm really digging that. So, we're going to talk about what this paper actually is doing. We're just going to call this Chalk Talk. That talk 403. Yeah, this one's not as good as the red. The guys at Disney Research took a look at rendering of clouds, rendering of basically the volumetric medium, and said, you know, these renderers are taking like 24 hours to get a good looking cloud out. I wonder if we could possibly use something to speed that up. And before we go into it, we need to talk a little bit about it. This paper is a very good paper. They go into a lot of detail about exactly what they did. And it doesn't help if you don't understand volume rendering. So it took me a while to actually plow through it in here. So I'm looking, there are some questions in here, especially about scale and mean path length and stuff that hopefully we can figure out together. We'll see. But first, we're going to get some basic terminology going. We're rendering that have a sort of participating medium. So we've got a poofy cloud here. There's actually a whole bunch of little teeny water droplets that are near transparent. Actually about the size, approximately about the size of the wavelength of light that's going through there. So, you know, to a scale or so. Really cool math that goes on here. A very diffuse material like marble or something like that, you can have scattering models that are fairly simple. Look out of it. And you have this very fine droplets of little teeny transparent pieces of glass, basically, that are light except for bouncing it around. And so there's this whole theory of what light does inside the cloud pans, right? In fact, they even have this thing. There's this lie, or is it Lee? Mie.
Scattering.
Mie.
It's also probably better to say, it's not that the scattering functions are complicated, it's just that it requires different sampling.
Well, are complicated. I'm gonna bonk you out on there, like.
But you know, like a BSS-RDF is really complicated.
It's smooth at least.
That's sampling, right? That's my point.
Okay. Well,
yeah.
Two sides to the same thing.
Yes. Yeah.
So think about what happens. Comes along and hits one of these water droplets. There's a couple of things that can happen. First of all, it's not a water drop, it's a dirt. The piece of light can be absorbed. If that light hits that water droplet, bam, it gets absorbed, nothing else happens. And it's going through a little bit different. It can be scattered. And this is where some of the details come in. A piece of water droplet and gets scattered. Well, obviously the light gets it bounces around a little bit and then comes out of many directions. And we're going to assume that it just comes out in one direction. Start looking at this as a sort of, you know, there's lots of photons going on here and lots of light hitting this particle. A distribution of basically what's the probability that it's going to come out in that direction or this direction or that direction. Where some of these models come into play. If it was a uniform probability that light would come out in any direction, circle distribution, right? Very easy to model. It's the light goes in an even particle. A sort of a backscattering distribution where the probability is, I'm sort of drawing this where the size of the circle matters. Comes in here, there's a higher probability that it's going to come right back out the way it came in. Scatter model, and naturally you'd expect that if the like this, and I'm drawing these forwardly, these have to sort of be normalized and everything, but it's more likely that the light is going to go forward through this than it is to go backwards. You have these guys who did this a long time ago. They kind of figured out how light scatters in this. Particle strikes a particle, and this is where the Lorenz-Mie into play. That's it. So it looks, and I'm going to do a horrible job at drawing this, but it looks kind of like this. Up there, for whatever reason, way more likely to get scattered forward. There's another clip, and it's symmetric. Symmetric, and then, oh, but it doesn't like to backscatter, so it has this little wiggle and little happy fish. Swordfish. Scattering fish. Peace said, not a complicated function. Well, it is a little complicated function, but that little nose is a pain in the butt. So if we want to accurately figure out where light is going, sample this. There are all sorts of parts of this thing that have dramatically higher probability than other parts, but all this stuff has interesting distribution, right? Sampling this becomes a real pain in the butt. You really have to put a ton of samples over here, but you can't forget about over here, and all of a sudden you're starting to sample this like a ton just to figure out what the light is doing when it goes through and hits this particle. One of the things they say, right off the bat, no matter what, is a pain in the butt. Do not care about this. We do care about it, but what we're going to do is approximate it with a clipped dots here. They're going to saw off that nose like that to make it just more computationally tractable. It still looks pretty much like a cloud, but makes the a heck of a lot easier. This is just an assumption they make throughout the program.
They split it. Multi-scatter on the.
I haven't gotten there yet, but you are right. Nafis is going a little bit ahead. This is kind of the we're assuming there's a cross here. Let's actually talk about through.
The other interesting thing is, you know what that peak gives you, right? The silver lining.
Right.
Without it, you don't get silver lining.
Absolutely. This is what's happening. If you've got sun, if I'm sitting over here, if I've got a cloud going into this direction, so here's my observer, and I have the sun in the background here, piece of light that's coming through this cloud, and a good chunk of that light straight through to my observer, and let's assume that that's going right through there. Blob right here is going deep. It's going into a deeper area. That's crazy ass little funk over, and most of them bounced around. There's enough bouncing that happens. So we're going to explain this in just a moment, because we want exactly what's when it goes together. So this paper, or the other link that I had to this chalk talk, was light transport in participating medium. Much referenced dissertation by 6. I don't have the name exactly in front of me. It's in the link. Really nice dissertation. This dissertation is so pleasant. Nicely explains what happens through to light in a participating medium. So the thing that I wanted to talk about and continue to talk about is exactly what we were doing there. In striking some particle, absorb, or we could have in the case of something like fire, if your participating medium is glowing, then glowing off the particle. Or you can have scattering. Out scattering, where the light goes through, the light hits this particle, energy of the light goes in one of these directions. Or, it's kind of cool, you have the particle, you don't even care about this light, in scattering. So this is light coming from other parts of the participating medium that is going in there so that it goes forward away from the particle. All this is directionally based. So we have this thing, goes through and gets absorbed and stops. Light that goes through, and then more light is directions, but we are really more concerned about light going straight through this thing. We have light that's going in and gets into the medium. Some of that will make it actually all the way through, but a lot of it will go in different directions. Instead of light just coming from there, we have light coming from all so that it travels in that direction going forward. Scattering. Is basically trying to figure out in all its forms, hitting this point in space, going in this direction out of it. Means zero. Emission means, well, however much it's glowing is going in that direction. Well, it might go in that direction, or it might actually go in this direction, but there's a probability of how much it actually goes. And then finally checking all the, and figuring out how much of that in-scattering is going in that direction. So it's all about going forward. This is, at its core, a rendering problem. Here, we're going to shoot a ray and hit points on the cloud. Now, what we're really interested in is going towards our observer. The light that's going off into this direction that we can't see, we don't care about. We only want to see, at this point, how much light is actually smacking into the camera plane at that point, right? So now, finally getting to the silver lining kind of thing, kinds of scattering that we want to care about. Right where the light source, hitting medium, single point directly scatters. That is a single scattering event, and it really is kind of this outscattering probability. On the other hand, there's this in-scattering. Well, where's all this light coming from? The light is coming from points in this cloud, right? It's another scatter that's happened to scatter into this that happens to be pointing in that direction. Draw these crazy light that eventually make it to this point and bounce in the direction of it. And this is referred to as multiple scattering. Is the scary thing, right? You have all these individual points that are having scattering events that all have that crazy fish shape of stuff. And you're basically asking this kind of impossible question, right? It's going into the cloud, the paths of the light, exactly how much ends up here and scatters in the direction of our observer. No wonder cloud rendering is hard. This is insane. How do you do this? We're not going to be talking about this. We're going to assume that you can do this. Most of them are. I hear this word all the time. Assumptions about, what your media. All right, I'm going to just bounce things around. I'll do this multiple passes where I'll bounce some stuff around, then I'll collect it around again and bounce it around again until I stop. The light stops changing as I bounce stuff around. A lot of stuff that you have to do to render this kind of cloud correctly. This direct scattering pass is actually pretty easy. It's a relatively quick thing to do because you're just bouncing it through there, again, using a sort of Monte Carlo technique. Full scattering stuff. It's a pain in the butt. Yeah. Try to use machine learning to accelerate this thing. Speed up. Yeah. In the worst case, they have built a machine learning system that runs where instead of a 24-hour render, it takes 12 hours to render. In the best case, it runs like 300 times as fast. Magnitude faster. Pretty damn good. So that's what we're going to try to figure out today. We're not going to talk about this, first of all, because I'm not up to speed on the latest techniques on volume rendering. Think about this. Say we do have a way of rendering clouds, and we can take time to actually render a dip. Can we use that data to train a machine learning so that we can render clouds faster? These guys, yeah. Twitch, and in case you haven't looked at it, I'm gonna start up presentation mode on here. Hopefully, life size is still working. Presentation input to this. See, right, you guys. Let's see. Screen. There we go. There we go. That's what I wanted to see. Press hide. If you haven't looked at the paper, it's this is the image that I was giving you, and so over here, the side of the cloud, this is the long render. This is the hours and hours and hours long render. They're which is 9 minutes compared to hours and hours and hours. And lengthwise, proud of this. Notice you're getting that silver lining kind of look. Here, the cloud, even though it's kind of hard to see here, is still very nice. And in fact, we're going to scroll down here. That multiple scattering thing actually takes time. So this is a real world rendering. Multiple scatter to a cloud that looks very gray. It's just there. Multiple scattering bounce around that interior glow of clouds, that sort of coming through. And also pay very much attention to this. 4 interactions, 4 multiple scatter bounces, almost an hour. Starting to look good, starting to look like a, at least maybe something that looks like a cloud. Really? All right, maybe this is good enough. No, we'd want to wait till it converges. It actually stops changing as you bounce light around hours. That's a sad number for just one cloud. Away with that, go away. And again, here's some multiple scatter, the models of scattering. So here, an isotropic phase function. This is basically a sphere that I was drawing. The phase function that looked like a fish is this guy. Go, oh, this phase function is any of that cool detail. And in fact, no silver lining. But here, all that sort of crispness of a cloud in some of these areas, if you can, it's smooshed out and filtered out. But as this sort of distribution of how light gets scattered, this one's not bad. It's easier to model, but this is the beauty. This is the one that really shows off. And if you zoom in on the distance, and then this is where they chop the Lorenz-Mee thing, and you do get a hit, but then if you add in direct illumination, it comes right back to the original one. So we're happy with this. They're just basic renders. We haven't even talked about machine learning. And here, by the way, is the fish function. Forward scattering model, and then the blue line is the crazy fish function. Swordfish. This stuff, the math. Well, we're going to keep this up because this is important. But I'm going to switch back over on presentation mode. You can see me. All right, so far so good. All right. Without any math at all, what are they trying to do? Build something that, given a fluffy clouds, a point cloud, what is the so there's a point X, W, right?
Hey, Doug, we can't see your whiteboard. It's still in presentation mode. It's like,
Oh, okay, my bad. Sorry about that. Thank you very much. Yes.
all right. Yeah, that's good.
Cheers. Thank you. Please yell at me if I never do that again. So it's basically saying, here's a point in space that is going into that point. We want to know how much light is actually coming out in that direction. That's the goal. Doing this properly, you have to do an interval. For multiple scattering, we're not doing the absorption and emission stuff. We're just doing that multiple scattering. This sphere, and here's your phase function. Dot W hat X W hat hat. It's reasonable to just take a look at this. This integral isn't all that hard. Think about what we're doing. We have a point in space and we have a sphere around it. Going through and saying how much light direction. So that is this. The direction here is W hat. And so we're going through and moving. This is the variable of the integral. And so we're just sweeping that around the sphere, saying how much light is coming in this direction? And how much light is coming in this direction? Phase function. In this case, it's a spherical phase function, but this could also be our fishy phase function, right? With a little. How much light is coming in? Then we know how much popping out in this direction because we have the phase function. So, right, you're just and looking at how much light is entering the phase function, which tells us how much actually makes it through in the direction that we want it to go. That's the math that the actual renderer wants to do. Now, right off the bat, they said, and actually model this with machine learning, to do this full-blown thing, because the multiple scattering and the direct scattering, the multiple bounce stuff and the single bounce stuff, really different mathematically. It's stuff that's traveling this crazy path through this cloud and gets all smoothed out. It has this smooth nature of it. And by the way, machine learning works better with smooth stuff than sharp stuff. Scattering is much more spiky. And you can even see that. You have multiple scattering because the single is so through. You'll have a very bright spot because the single scattering can make it through without getting bounced again. So here's some sun. Don't try to do both. And in fact, they have this really cool graph of what happens when you try to do both at the end. If we get there, we'll try. Actually do this. We're going to break this up into U or L, X, comma, W hat, L, direct, W hat. This term and replace it with this term. Skip this thing. Skip it. We're going to do this data, we're actually going to suck out the direct component. Because all we want to try to do is model this multiple bounce. And that's an important part. And this way, we'll just add back in using normal rendering techniques, which actually aren't all that expensive. So a huge part of this first thing. So now, yeah, you can think about this and you can say, all right, 80 clouds. And I'm going to get 80 computers to do this for 34 hours so that those clouds converge. Special renderer, because not only am I going to render it, but I'm also going to save all this information. Point, I have the luminance or the radiance of this point in a whole bunch of different directions. I'm basically going to take a whole bunch of clouds and build myself a data set to know what the radiance is at this point in this direction. Or if I wanted to know what the radiance is at this point in this direction, I can just look it up. 80 clouds of varying shapes and sizes and render the heck out of them. Database of what clouds look like. Now, they mentioned at the very end of the other machine learning algorithms, if you wanted to render clouds that don't look like these 80 clouds, something that is completely different from your data set, you need to retrain this thing. This thing is going to render clouds that look like clouds that you've already rendered. Make sure that this works so that even if you have a cloud that is in this general family of clouds, it still looks good. So how do you do that? Well, we have to figure out what kind of data we need to sample. So, how do we, the cloud? And this is one of the key insights, right? This is the sort of thing that they said is represents enough information that given an arbitrary cloud and an arbitrary point on that cloud, we can get enough information that sort of uniquely classifies what's going on in that cloud. Cloud, what do I need to know? Well, I need to know some neighborhood stuff, right? I need to know, this is all about multiple scattering, how light is actually bouncing around and getting to this point. Point deep into the cloud. Or is it on near an edge of the cloud? And what's going on? If there's a lot of detail around this, if there's a lot of little poof ball here and a little poof ball there, that's going to change the way the light is actually going to bounce around. In fact, if I'm deep in the cloud and I've got a uniform distribution of cloud around me, if I'm over here, air gaps between here and here, the light that exits here and then there, that's going to be different than here where all its neighbors are uniformly cloud. So that's where they started thinking, you know what, we need to sample a lot of stuff. The cloud looks like on a really big scale. We need to know what the cloud looks like at a scale like this. Now, I drew this box in a little weird way, right? I kind of drew a diagonal box. Oh no. That's somebody else. I drew this box in a little diagonal way, and then you're going, why did you draw it like that? Why didn't you draw a box around the entire cloud? Important information that they kind of discovered. Where's the light source? It doesn't have to be a sun, but let's say the light source is over here. Directional. So we actually want to orient this in so that a lot of the data is pointed in the direction of the light source. So let's start sampling this, and we'll create a box that's fine. Sampling the cloud and say it's 5 by 5, and let's create a little 3D box here. 9. So 5 by 5 by 9 box. The densities. Actually draw. There's 9 points here, and so on. So there's 5 by 5 by 9, which is 225 distinct samples we're basically going to sample the density of the cloud at that point. If you're out in open space, the density would be 0. If you're inside here, the density might be, you know, a lot of cloud. So this gives us a snapshot of what the cloud looks on a really big scale. But that's not enough. If we just use this, we're not capturing a lot of the detail that's nearby. And when we get close to this, the detail that's nearby this point is actually important. So they started saying, okay, well, wait a sec, let's do this multi-resolution. Multi-resolution works great in a lot of computer graphics things. So let's take this and then use the same stencil in the same orientation, but shrink it down a bit. So we're going to cut it in half. And so this is supposed to be half the size of that. Still 5 by 9. Got 9 points here. Perfect. That's 9. And then we're going to cut that in half. And we're going to cut that in half until eventually we get to 10 levels of scale. Essentially, they have a k equals 1 all the way up to 10, where the scale is 2 to the k, right? So you end up with a lot of samples of density. And as you start off with a density that hopefully will capture, and quite frankly, I'm not even sure if this is kind of the way they drew it in the paper, but you quite frankly might have a box that completely encompasses your cloud, or the box itself is oriented so that it's centered, well, is here, there's more, this is the 5, is more heavily weighted towards the direction of the light source. And they have this way of doing it. They say, take the z-axis to be pointing towards the light source, and then the x-axis is pointing towards your observer. So here's my observer. And then the x-axis isn't pointed towards that. You create a plane between the light source and the observer, and that cross product is the x-axis. And then the cross product of the directions of the sun, the x-axis produces the y-axis. And so that gives you the orientation of your sampling stencil. They showed why this works. In the back of the paper, they talk about doing this with a uniform stencil where it's 5 by 5 by 5. Did not work nearly as well because this extra data over here characterized a lot of the clouds that was pointing in the important direction of the sun. And they also tried other resolutions. And quite frankly, this resolution and some other schemes for doing this sampling thing, but they were happiest of all with 5 by 5 by 9. It's working well in the machine learning community because it's all about picking numbers that seem to work. All right. Capiz is laughing. He knows. All right. So now, what are we doing? Well, what we're basically doing is producing a characteristic. So let me see if I get this right. So we define an efficient descriptor I of x, represent our cloud without excessive computation and storage requirements. So what we'll end up with is a data set. This is deep data set, and they call it DN, which is a Python list of tuples, which is our descriptor of densities of what's going on. And there's one other thing they add to that, and we'll show you what that is in a moment. And then that corresponds to the radiance at that point in that direction. Comma, Z2, comma, L, X2, W2, comma, Z 1,000,000, comma, L, X 1,000,000, comma, W 1,000,000. I'm just basically emphasizing that you collect a lot of data. So what we're ending up with is density descriptor after density descriptor after density descriptor direction, randomly choosing points on this cloud, not quite randomly either. They have a very defining which points are more important than others for training machine learning. But basically for now, we're going to choose points on the cloud, choose directions that we want to go to, sample the density, build a descriptor. And we're going to build a huge number of these. You know, I said we're going to only render 80 clouds. But now you can think, well, those clouds actually have a ton of data in them, right? If we start plopping around here and grabbing point after point after point, we have, with these 80 clouds, we can build a lot of what the cloud looks like in this general neighborhood and how much light is actually heading towards our observer in that direction. Now, I'm going to stop one moment here. In the highest level, covers 2 to the 9th. You know, it's this thing. They actually go from 0 to 10 or 9 instead of 1 to 10. I'm sorry about that. I thought it was. But the biggest stencil basically covers 2 to the 9th scale from the smallest stencil. I'm going to read a little section. In order to make the scale independent, stencil dimensions and density values in terms of the mean free path. Scaling the cloud geometry and density such that 1 unit of distance corresponds to 1 mean free path density of the cloud. I don't quite get that. Now, I do know what mean free path means. The distance of a thing would travel before thing. So Wikipedia actually has, go to Wikipedia and you go, what the hell is mean free path? So if you have a very dense material, the mean free path of that dense material is very small. If you are starting from a particle and how far do you have to go before you hit the next particle? And so there's sort of a average distance where, you know, the probability of within this distance is really high. It's that mean free distance that you have to go before you strike something. You've got a box with a lot of particles, the mean free path is going to be half a nanometer. You're going to bounce really quickly. But if you have a box that's a vacuum, the mean free path is enormous, right? If you have a big box, you're going to have to travel kilometers before you hit another particle or have a high probability of hitting another particle. So this actually makes sense, right? They want to make sure that the data that they're generating at a really small scale correspond to a data really large scale. And so you can kind of think of, oh, this is very clever. They're trying to scale the density and the geometry of their cloud so that this data and the big data actually work well together. Don't confuse the thing. I think there's some supplemental material for this paper that I haven't read, and I hope they explain it better because I see what they're trying to do. I just don't understand exactly how they try to do that. So heads up for people who are going to implement this after watching my stupid chalk doc here, you don't have enough information. There's something going on here that you have to figure out for yourself. It's an exercise for their. All right, but they do that. Keep that in mind. All right, all the stencils share the same local frame centered at X, and I talked to you about how you build the frame. The stencil level is formed by 225 points. Got that called. Of the box skewed in the direction of the light source to make sure that it works out well. All right, now we've got this. We've got our data. We built it. Now we have to feed it into a machine learning thing. Right off the bat, machine learning things. I've been on a tear with convolutional neural nets, CNNs. Convolutional nets for image processing is where it's at. Neural nets. And they said, don't try convolutional neural nets for this. In fact, simpler neural nets are a lot easier because convolutional neural nets have this sort of inherent multi-scale built into them. And we're not going to go into that. But if you put convolutional neural nets on top of our already multi-scale descriptor of how this works, you get into trouble. It doesn't converge very well. It will work, but it doesn't work nearly as well as a more simpler neural net. And so what we're going to do is build a multi-layer perceptron. You guys remember what a multi-layer perceptron is, right? And what we're going to do is really weigh the thing up. So first of all, the first input layer consists of 155 elements. So what we're going to do is actually take the densities, first biggest layer or biggest sample of our cloud. And then we're going to hook it up to a, make sure I get this right, using a standard neural net system, where we're going to have over here, this point here can see all the values of our input. And each one of these guys has a weight associated with it. Weight. Here can see all the values of our input thing, and there's weights associated with this one. Weight. There's a bias. There's 0 all the way down to a bias 255. And so we end up with, this is all within a, and they use the RELU, the restricted linear unit, or rectified linear unit thing. I'll draw that out for you. This thing is F times W 1K OK minus 1. And K minus 1 is that. Yes. Nope. Take it back. Nope. That. OK minus 1. Sorry. Just making sure I get this right. Each block processes the corresponding stencil level and denoted angle. Oh, and by the way, the one other thing that they do, it's the stencil level is all these things, and they also add in an angle gamma down here. That is the gamma is the angle. Oh, you also add the angle gamma, which is the cosine between the input and the from the sun to the viewer. So it's basically a representation of where you are in the phase function for the output of this. All right, so that gets thrown in there as well, so that the neural net knows which direction you're looking at. Because at this point, the neural net knows the densities, and it's kind of oriented towards the sun, but it doesn't know where the output is going. And so we're putting that in to say that the output is going in this direction, right? Okay. This, all these weights on here can be represented by a great big rectangular matrix, right? In this case, I think it's square. Square matrix, where each one's applied, and you take this vector and you multiply by that. So that is what the W is. And then you add the bias to it. Bias. All right, but we're not done. There's also each block K processes the corresponding stencil level K and angle. So that's this stuff. And this is, oh, right. Sorry, I've done a bad thing here. This is actually VK, ZK. I've kind of screwed up the terminology. This is VK. Oh, these. W1K O8 plus bias 1K. Wait, what? What's that? This is the clever bit. Something that they are doing that was terms of making this work for the clouds. Neural net, what you have is inputs that get connected up into hidden layers. So hidden layer 0, hidden layer 2, and so on. And then eventually you have an output layer. Right? And inside here, you have this massive network of connections, and it gets there, and you can even have these reduce the size of the neural net and all sorts of stuff. But you basically have input, and then the data travels through, and then goes to the output. And then you have the standard way of training neural nets, where you see if the output is what you want, and if it isn't, you go back and change all these weights throughout here so that the neural net gets better and better. They said, actually, that's not the greatest thing for this, because we have a lot of layers here. We have 10 different layers that were going on here. And it would be nice if every single one of the layers had sort of an unobstructed view to the layer before it. And so they said, let's do this. Let's not only take this input, layer in these layers as we're going there. So think about what they're doing. The first layer is the highest resolution, high res, or the biggest resolution. So actually, the largest layer of samples. So big densities. Density. We don't want to just stop there, right? We want to also sneak in the next sampling of data. That's what that bad boy is. So not only do they take this thing, which is the VK, that's the layer that we're working on, but we're also going to take the next smallest, K-1 density, and we're going to connect it up too. So we're going to make another input layer be sliding into here. So this layer here not only sees the input layer, which is the highest density layer, but also sitting over here, waiting to be used, is the output K-1, which is the next smallest box there. So we're going to slide this in here. We're going to connect these guys up in the same way. We're going to have all these connections going here, and these are the W's. Are the W's that we're going to try to compute. So on the very first layer of this thing, it can see the density of the biggest box and the density of this. And then we have the bias, which is standard in neural nets, and then we have this little function here. Whatever values these add up to, and compresses them into, this is the nonlinearity of the function. And the function here looks like that. All right. Actually pretty cool. Coolness, right? There's another special layer, and we're going to use a different pen so that you can actually see it, where they say, you know what? But it would be extra special cool if we could kind of keep this going. So what, this one be more. So we're going to add another layer here that can connect up to all these guys. And bam, 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 bam. And this one is just a normal neural net, except it doesn't have the activation unit. So we have more W's. This is a W2, actually. W2, W2, W2. There's a whole bunch of W2s here. And another bias, bias 2, all the way down to bias 2. And then,
what weights do these W's represent?
there's another, but there's no activation unit here. Just another big linear transform that we're going to take to this layer. And then finally, we still haven't even produced our output. The actual output is this layer plus this layer. So this guy goes over here. This is OK minus 1. And then you run this through the, you run the addition of this through another activation unit. So I'm explaining this poorly, but kind of clever. So we take the input, the biggest density layer, tacked onto it, also the next lowest density layer, and use that in our first hidden layer to produce the output that we want. And this would produce a whole another number, 255 numbers. We want to add another layer. And this is just, often you'll do this in neural nets. You'll add an extra layer to get more nonlinearity. You get more control over it. But this is kind of cool, is that you take this new lower layer over there as well. You're actually adding these two values together. And this is a big thing called a residual connection. And you're like, well, wait, what? Okay. Think about what's going on. It's just the densities of this. Once we get past this, we're now into the depths of our neural net. But we have to have a way of sliding in the ever-decreasing layers of, or samples of density. Here, we're going to take our first layer, connect it up, and notice how we're connecting it up. All these values are getting multiplied by W's or V's to get to this layer. What they say is, not only do we do that, but we're going to take the raw values of the next lowest layer and just add them, not multiply them by anything, just add them to this layer. And then, once we do that, we start it all over again. We have a duplicate of this guy now. So this is F sub A, and this is B0 it's connected up to this. And then we have this plus O sub K minus 2. And this is our B2s and B2s. These guys are all connected up, right? Connected up. And this gets the F applied to it. So this is the way they're feathering in each lower resolution sample densities. So we have the original input that just goes straight into it. But then each time we take the next lowest input and combo it into there, but then we also use the next lowest input in its form and add it to the output here, so that we just sort of layered on the next lowest input before we hand it to the next block of our neural net. And then we do it for the OK minus 2 This was invented by Microsoft back in 2015. They developed this residual connection where they not only took the input, but took another lower level and slid it in, so it just sort of skipped over. Went in here, it got by all sorts of W's, but then they took the raw values and stuck it into another part of their neural net. And those raw values aren't multiplied by anything, so this part of the neural net can actually have access to those raw values. And then they get multiplied, and then the next level gets crammed into here, and the values get pushed around. This residual connection was came up, and Microsoft created a neural net called ResNet that was really good at identifying images. These guys grabbed that idea and said, you know what? We can use that to cram in our ever-decreasing density samples. 10 different blocks of this, and it goes on and on and on. Connections where each time one of the lower resolution ones, the smaller resolution densities, get crammed into this. I have a hard time explaining all this, but basically this is a really, really cool idea. As you slide through here, you have the power of the neural net, but you also aren't forgetting about the fact that you've got raw data being pushed into here. Neural net, sort of the ability to see the densities around it. This point of the neural net have what came from the highest density, but it also has raw information from the next lowest in density. So, and I'm looking at the, I'm going to switch over to the, if you look at the paper description of how this all works. So, in terms of training this thing, it's pretty standard. They're using an atom solver. They're using least squares, convergence at the very end of this entire neural net. Layers that they're just normal multi-layer perceptrons that scrunch the data down into the radiance that they're looking for. It works. It actually converges really fast. Like I said, if you look at the back of the paper, there's all sorts of discussion about why this configuration seems to work the best. Stunning results. They're getting, first of all, the images look really good. And where's the table that describes how fast this thing works? There's a lovely table that says they're getting, here we are, clouds, depending on how it's lit, they're getting speed ups of 4,000 times faster in some cases, 3 orders of magnitude faster. I is 41 times faster. And also, one of the things that everybody asks when you read this paper is, yeah, this is cool, but it doesn't hold up when you start animating the clouds. That is, they are super extra proud of how well this holds up when you're animating clouds, because this is a huge filter. What it's doing, modeling the multiple scattering that's going on in this very tuned nonlinear filter that's going on here. And they say, this sucker holds up temporally like nobody's business. It is, they're very actually proud of how fast or how well this holds up as you animate around the cloud. And then you can go to one of their websites and you can see the results. Shape, you can animate around the cloud and it looks beautiful. And they do say that there are still some issues with noise. You have to let this run a little bit and converge a little bit, but, and in fact, some of the times when it isn't as fast as when you have to let it take extra samples. And it isn't free, right? You want to know what the radiance is at that point. 255 times 10 density samples. But quite frankly, compared to multiple scattering, that's cheese. Since I don't know, hopefully this is a good introduction to this paper. It was really clever. The convergence properties of this thing, by the way, were pretty hot. They showed some graphs of it converging. It seems like it's a dead simple thing that this will just work. Putting it together, I didn't see a GitHub account for this sucker, so unfortunately that's not too good. But this is a nice. I'm impressed with this. And they're getting some amazing results. The one thing that they did say, by the way, this works for smooth things. It works for clouds. They do not work for sharp shadows. So they had a test scene where they had a spherical cloud standing next to a cube cloud. A proper render go, you get this nice dark shadow on this spherical cloud. Their shadow is like crap. It is just not trained for that kind of stuff. Typically train it for this, and that's really, really hard. The shadow is a very specific thing. You'd have to have a ton of data on it. They were like, they had that standard trick in papers, like, we have ideas of ways of addressing this, but we haven't done it yet. So maybe they can do it. So, all built in TensorFlow. Building this thing, not very hard. Actually, not very hard. It's just putting in all the details, I think, is actually the hard part of that, putting this all together. Like I said, this is only for multiple scattering. They also have a Monte Carlo thing to do the direct scattering to make sure you get that nice mode to clouds. Thank you very much. There will be no Chalk Talk next week because I'm traveling, but there will be one the week after that, I think. So, there we go. Bye-bye. Did that make any sense? Sort of?
Yeah.
All right.
I don't get that. That looks so coupled together.
It is, but it actually does make sense. I highly recommend reading the paper.
And then
So if it's just a render time is just a